Welcome to where gaming dreams become reality, a GPU fabrication facility. Today, I'll show you exactly how graphics cards are made.
Every graphics card begins here, with quartz, one of Earth's most abundant minerals, destined to become the purest silicon. This refinery will transform ordinary quartz into the purest silicon ever created, the foundation of every GPU. Arc furnaces unleash temperatures hotter than lava, breaking molecular bonds and liberating pure silicon from quartz.
Liquid silicon, flowing at over 1400 degrees, begins its transformation from raw material to technological marvel.
As silicon cools, its atoms arrange into crystalline structures. But this metallurgical grade is only the beginning.
Etched. Chemical vaporification removes every impurity, achieving 11/9 purity.
Inside Siemens reactors, silicon grows atom by atom onto heated rods, building the purest solid material humans can create.
These polysilicon rods represent months of growth, each one worth tens of thousands of dollars. Carefully broken into chunks, each piece of polysilicon will contribute to thousands of GPU dies.
Inside the Chokralski furnace, we'll grow a single perfect crystal, the foundation for millions of GPU transistors.
Over 3 days, a single flawless crystal grows Krunti, large enough to yield thousands of massive GPU dies. A perfect silicon crystal, soon to become the hearts of graphics cards powering games and AI worldwide. Diamond wire saws slice the crystal into wafers thinner than 2 stacked credit cards, with atomic-level precision. Every wafer faces intense scrutiny. Surface imperfections invisible to the eye would destroy billions of transistors.
Lapping removes saw damage and creates surfaces flat to within a fraction of a human hair. CMP polishing creates surfaces so smooth, individual atoms would appear as mountains under electron microscopes.
Sequential chemical baths remove contamination atom by atom, because a single dust particle would ruin thousands of GPU cores.
Spin drying at hurricane speeds leaves surfaces perfectly clean. Not a single water spot or particle remains. Thermal oxidation grows a perfect glass layer, the insulating foundation that isolates billions of transistors.
Ellipsometry measures oxide layers just atoms thick in Zevern, ensuring perfect uniformity across the entire wafer.
Molecular priming creates an invisible adhesion layer perf, essential for the patterns that define every GPU transistor. Photoresist spreads into a film thinner than a wavelength of light, ready to capture circuit patterns with atomic precision. Soft baking drives off solvents purin, preparing the photoresist to capture patterns smaller than viruses.
Sealed in protective pods, wafers travel through the fab, each one carrying the potential for thousands of GPUs.
Overhead highways transport wafers worth millions of dollars per day. A ballet of automation that never stops.
The ASML EUV scanner, 180,000 components, costing $350 million.
50,000 tin explosions per second generate light so extreme, it must travel through vacuum. Even air would absorb it.
The reticle, a $200,000 master pattern encoding billions of transistors that will power graphics rendering. The wafer stage positions with accuracy measured in atoms, stopping and starting faster than any other machine on Earth. EUV light, reflected by mirrors smoother than anything in nature, prints GPU patterns smaller than viruses. Building a GPU requires over 80 patterning steps, each perfectly aligned, each defining features smaller than viruses.
Post-exposure baking amplifies the light pattern emission. Chemical reactions complete what photons began.
Developer solution washes away exposed resist, revealing the pattern that will guide GPU fabrication.
Electron microscopy inspects billions of GPU features. Any defect could kill thousands of shader cores.
Plasma etching, ions accelerated to incredible speeds, carve GPU circuits atom by atom. Atomic layer etching removes single atom layers of Murbic, achieving the impossible precision that makes modern GPUs possible. The protective resist served its purpose. Remove
Hundreds of measurements per wafer maintain atomic precision process control, essential for GPU yields.
Ion implantation fires dopant atoms at incredible speeds, creating the electrical gradients that make transistors switch.
rapid thermal annealing activates dopants, reaching temperatures that would melt steel, lasting only seconds. Gate dielectrics, just atoms thick, grown one atomic layer at a time, enabling the dense transistors that power modern GPUs. Metal gates enable the fast switching that makes GPUs compute, deposited atom by atom with perfect precision. Gate all-around transistors, 3D architecture where gates completely surround nanoscale channels, enabling unprecedented GPU performance. Low-K dielectrics separate copper highways, reducing the electrical interference that would slow GPU computations.
Planarization creates atomic flatness, essential for stacking over 20 metal layers in modern GPUs.
Dual Damascene creates the vertical and horizontal connections, building the highways that carry data through the GPU.
Copper fills billions of interconnect pathways, tunso, the highways carrying data at near light speed through the GPU.
Polishing reveals the interconnect pattern, billions of copper traces forming the GPU's nervous system. Over 20 metal layers, more than 100 kilometers of copper traces packed into a chip smaller than your thumb. Protective passivation seals the GPU, shielding tens of billions of transistors from the outside world.
Wafer probing tests every GPU die, billions of transistors verified through thousands of simultaneous connections. The wafer map determines each GPU's destiny. The best dies become flagship graphics cards, commanding premium prices. Every GPU receives a unique identity, traceable from silicon to gaming rig, for its entire lifetime. Diamond blades separate thousands of GPU dies, each one a complete graphics processor ready for packaging. Pick-and-place robots position GPU dies with micrometer precision, beginning the transformation into graphics cards. High-bandwidth memory stacks work. Through-silicon vias create thousands of connections per stack, delivering terabytes of bandwidth to the GPU.
Reflow soldering creates thousands of connections in minutes, through each joint essential for GPU performance.
Underfill epoxy protects thousands of fragile connections, enabling GPUs to survive years of thermal cycling. The heat spreader will conduct hundreds of watts of heat away from the GPU, essential for gaming performance. Final testing pushes every GPU to its limits, determining whether it becomes a flagship or mid-range card.
Burn-in testing accelerates a year of aging in days. Only the most reliable GPUs survive to reach customers.
Every graphics card proves its gaming performance. Comprehensive testing ensures flawless operation from unboxing. Sealed in premium packaging, graphics cards begin their journey to power gaming experiences around the world. From this distribution hub, millions of graphics cards ship to power gaming, AI, and creativity worldwide.
And that's how a GPU is made. From simple sand to tens of billions of transistors, ready to render your games at